3 first on page 127. So you all good now with the converting between degrees and radians? It's not that difficult, is it? All right. And they're quite nice to use, radians. And what we're going to look at next is the kind of proof that when we're dealing with circles, they're quite nice. Yeah?
Oh, so I fully understand why 1 division equals pi over 180. Because pi is 180.
Yeah.
So then it's just 180 over 180. It has to.
Yeah. Oh, right. Wow. You've discovered something. Stuff. All right, let's have a quick look at question 3. So like I said, Ethan as well, you can join us at this stage. So it says the area of a sector of a circle is given by area equals pi r squared beta all divided by 360. Now, because you've been working on this last, can you tell me where that comes from? You were working on this last lesson.
Where this comes from?
Yeah, so this is the area of a sector. You'll remember what a sector is, yeah? What's a sector then? Section of a circle. So, what is the form? Where does this come from? Ethan, do you remember? Because you were doing it last lesson.
It comes from
Where's it built up? Where do the parts of this come from? What would you have written instead?
for mine, it would just be it was the theta over 360.
Yeah, so theta divided by 360 multiplied by, that was an arc length, so the area would be pi r squared. So do you remember we had, it's a fraction of the entire circle, right? So theta out of 360 is the fraction of the entire circle. Now what we've been asked to do is convert that into radians mode. This is where everyone else can come in. So what can we do? So that's in radians. So what would we do instead?
Pi, or the area is equal to pi over 2 pi, so 1 half.
So it would be
Pi over 2 pi, which simplifies to 1 half.
why would it be pi over 2 pi?
Theta, so theta.
Okay.
That is pi r squared.
So we've got theta, whatever it is, whatever the angle is, it's the same idea, all right, multiplied by pi r squared. Now, what can we do at this stage?
Oh,
Yeah,
you can cancel out the 2 pi.
so we can cancel out the 2 pi's, and we are left with the area is a half of theta times r squared. So do you see how now, if I've got a circle and I'm working in radians and I want a section of it, how I've got a slightly different formula for working with it in radians. Yeah. So if I said to you that this angle was, well, let's say it's 30 degrees. What's that in radians? Okay. So this would be pi over 6. So the area of that would be just a half multiplied by pi over 6 multiplied by, let's say the radius is 2, so multiplied by 4. And what would that end up being?
60 degrees. 60, area is 60, sorry, 60 degrees.
Okay. So with the 4 and the 2 cancel, so that would be 2. The 2 and that would be cancelled because this would be a non-calculator style of working at it. So then I've got the area is actually pi over 3. Yeah? I've done that all right? Pi over 3 square centimetres instead. Alright, so I can leave it in that form now, that exact form, or I could give it to 2 decimal places. Very significant. Where did you get 6?
Maybe because you put like pi is 180, the 180 divided by 3.
No, I just said, okay, well, 1/2 of pi over 6, and pi over 6 is 30, and 1/2 of
Pi divided by 6 is not.
pi over 6.
Oh, okay, you convert it back to degrees. No, we don't want to do that.
I was going to say the area in just like 60 centimeters squared. Or,
But it's not, is it? What's pi divided by 3 centimetres squared as a number?
1.7. No, less.
So Ethan, do me a favour. We're doing this in radians. I want the area of that sector, 30-degree sector,
wait, why is pi?
2.
3 is 60?
2 centimetres. What's the area of that using degrees? You work that out for us.
Isn't pi over 360?
No, but wasn't the point of using radians so that we can cancel out the pi so we don't have to worry about decimals? So then
But
we're not
we
using it as an
haven't been
angle.
able to cancel out all the pi's because the angle
Yeah.
is now in pi. Isn't it?
Well, wouldn't the
So,
wouldn't the
yeah.
area of
Right. But what you're doing, what is pi?
the denominator over the circumference, I think? Or something?
It's just a number, is what I'm getting. Yeah. Roughly what number?
3.14.
3.14. Yeah. So what would pi divided by 3 be? Roughly, yeah. Well, a little bit more actually. 3.14 divided by 3 is about 1.1.2,
Oh,
Yeah.
something.
something like that, yeah? Now, don't get confused with pi being divided by something. It's always to be converted into a degrees of angle. Yeah?
So that's not in radians.
No, this is an area. If I convert it to a decimal, what do I get? You tell me now. 1.047 square centimeters. Yeah.
So you said pi over 6 was 30 degrees. Now
Right, but why don't you use 30 degrees as a 30 centimeters?
it was not saying.
So just because it's a pi divided by 3 doesn't mean it is an angle. Yeah? Pi divided by 3 is also just a number. That number can be, just like 30 can be an angle, it could be a measurement of length, it could be a measurement of time, it could be, depending on the units. This pi divided by 3 is not the angle anymore. Where was the angle used?
You get the formula?
Yeah.
How can the area be smaller than one of the lengths? How can that possibly be the area?
Well, if you have a square with side length of 0.5, the area would be 0.25 centimeters
Yeah.
Because you're not saying it's a length, it's an area. Now don't forget, what you might be thinking of is, but that's 2. So if I have 2 squared, that makes 4. So it's bigger, right? But that's the area of a what shape?
Square.
Square. But this is only an actual small sector of a circle, yeah?
If we did it in degrees, would we get the same answer?
Well, that's what I'm after Ethan doing. Ethan's in the process.
1.0. Or yeah, I got the 1.04.
So let's just go through it then. In degrees, what would be the process? So this is in radians, right, using this formula, but let's do it in this one in degrees. So the area is, this time, 30 degrees. 30 divided by 360, multiplied by pi, multiplied by 4 again.
So 4 pi over 12, 2 pi over 3.
So 30 divided by 60 is a 12th, yeah? A 12th of pi times 4, the 4 cancels, which makes it a third, so then we end up with the same thing, don't we?
Yeah.
Because the angle's been dealt with. When was the angle dealt with here?
And you put into a formula.
Yeah, but what did we do? This was the angle, wasn't it? The angle was part of a fraction. And when was it dealt with? Well, it was dealt with when we turned it into, well, it's a 12th of. So what does 30 divided by 360, why is it 30 divided by 360?
It's specifying that specific sector of the circle.
Yeah, so at this stage, isn't this already not an angle anymore?
Yeah.
What is it now?
It's a fraction of a circle.
It's a fraction of a circle. We just used that number, right, to figure out what fraction of the circle. And we do exactly the same thing if it's in radians. Yeah, so the pi divided by 6, as soon as I put it in there, is no longer an angle anymore. It's a fraction of the circle. Yeah. And because this, I mean, don't forget this is not drawn to scale. If this angle is 30 degrees, or pi divided by 6, it's actually can be quite small. And that only being 2 centimetres, this area, right, you're saying looks too small, but actually it's not a rectangle, is it? Yeah. Right? If we actually drew that to scale, it'd be really narrow at this end, wouldn't it?
Yeah.
And so it's going to be a small area. Okay, so the next thing, are you all right that with the area? So we've got there is a different formula now that we can use, potentially. What's the formula for the area again, if it was in radians?
Theta r squared over 2.
Yeah, a half of theta. There's a new formula in radians. Ethan, what's the formula in degrees that you're still using?
It is theta over 360 times pi squared.
Okay. So that's area. Now what I'm after now, the next thing we need to look at is this thing. Linear displacement. Alright, and we're going to come up with a formula for that as well. Alright, you know, it's in the book, but we're going to figure out where it comes from. Do you know what I mean by linear displacement? What's another way of saying it? Whether it's in degrees or whether it's in radians. What's a linear displacement? Yeah.
I assume it's like the perimeter of the circle. It's like straight back.
Yeah, do you know what I would mean if I said an angular displacement? Well, the displacement, an angular displacement is how far something has moved
Oh, yeah.
by an angle. So if I say the angular displacement is 30 degrees, what am I saying?
It's 30 degrees.
It's moved 30 degrees round, yeah? Now there's an angular displacement, whether it's in degrees or radians, but there's also a linear displacement, whether that's in degrees or radians. And what's the linear displacement going to be? Well, you kind of said round, but if I only do 30 degrees, what have I created? It's not the area of the sector, it's the, what's it called if it's only a bit of it?
It's like arc.
An arc, right. So linear displacement is actually we're looking for the arc length. Alright? We're looking for the arc length. So for instance, this is a beautifully drawn cycle wheel. Alright? So if that wheel travels through 60 degrees, how far does it go? So if we measure a starting point. Now, this is interesting because I was thinking maybe we can do this.
Well, it depends what's the radius of the circle.
It does, doesn't it? So, robots. What's on the side of the wheel?
The side of a wheel.
Can you see what's there?
One of those orange thingies
What do you think that's for?
to measure the linear displacement.
How many rotations we make, yeah? So I can program this, which I might get you to do. I'll tell you how to do the program, and you need to figure out how many rotations to get it to go a certain distance, right? Maybe next lesson. So if I rotate this wheel around 60 degrees, tell me when to stop. What? 60 degrees?
That was almost 180.
That's almost 180.
I'm sorry. Let's start again.
Right?
I wasn't
60
finished.
degree rotation.
60's like right there.
There.
Okay, right. It's a bit better. Yeah, your first estimate's absolute rubbish. So, what would I mean by its linear displacement then?
How much move? Sorry.
Ventriloquism there. Yeah. How much it's moved? Yeah, so the distance. So, we would have, if this is my little orange thing, I would then have a distance travelled, right? That would be my arc. If I roll that arc, it would end up moving to a point on the line, yeah?
Yeah.
So that would be my linear displacement here, that there. Right? In degrees, how do I know my linear displacement?
Calculating the arc length.
And what is it? Arc length is calculated by doing.
Oh yes.
T-Bone?
Theta over 360 times 2 pi r.
So let's simplify that. No.
Theta over 180
Theta over 180 times pi r. Okay? That's in degrees. Got that? So, Ethan, if my wheel is, how big is your mountain bike wheel? You got 29s or 27s and halves? You know?
They're funny, yes. He's my dad.
29 inches. Let's go with that. Mine are that big. I think the road bike wheels are 29-inch wheels. All right. 29-inch, and let's what?
The radius is 29?
No, the 29 inches is the wheel, the whole thing.
Oh.
Yeah.
I was about to
So,
say that'll be a massive wheel.
yeah. It'll be huge.
It's
So the whole wheel, the diameter of the wheel is 29 inches. All right. And let's figure out how far it would go if it's gone through 60 degrees. All right. Your job. You guys. All right. What you're going to do is you're going to. Hey, what?
Find the arc.
I want to know how far the wheel goes through 60 degrees. Okay, you guys are going to do it in radians and then come up with a different formula, simplified formula for it in radians.
Say less.
And so what did we do? So first of all, radians people, you converted 60 degrees into pi over 3. Okay.
870.
Okay, so then we can put our arc length is actually pi over 3 out of 2 pi multiplied by 2 pi multiplied by r, which is 29 over 2. Alright. Now that's super messy. Why is that messy? Well, I've got a fraction as a numerator. But here's the nice thing. By using radians, what can I now get rid of? So, the 2 pi, they just cancel out. I don't need to do any simplification. So then I'm left with pi divided by 3 multiplied by 29 over 2. Now, have you noticed what we've now got at that stage? That is a potential new formula, because what is pi over 3 in this question?
Arc line.
The angle, isn't it? Beta. And what is 29 divided by 2? the radius. Okay? So there's our new formula.
I
Just theta times radius, which is lovely, isn't it?
saw that and I was like, there's no way that's.
Yeah, that's it. But we've still got to finish because our linear displacement is what? Well, now we've just got to know how to multiply fractions.
25%.
So it's 29 pi multiplied by the numerators divided by 6. Now, so should we tell Nick how 14.5 pi over 3 was messy? How do we get it to be the same thing?
It's equal to the same thing.
It is equal to the same thing, so how do we get it to look the same?
Multiply the numerator and denominator.
Yes. Multiply 2, multiplied by 2, I get 29 pi divided by 6. Alright, so when we've got a decimal in our answer, we just need to find an equivalent fraction that doesn't have that. Yeah. And then, can we just confirm then, if you do on your calculator 29 pi divided by 6, what did Ethan get? What was your answer?
15.1.
15.18.
1.8.
Yeah.
And the units, please.
Inches.
Inches.
Oh,
Thank
okay.
you. Inches. Not one we normally use, but I gave you the questions in inches, wasn't it? All right. So there's our another new formula then. So summarising. Do it on the wrong page. No, I didn't. All right. Summarise then. We've got. Where's my formula? Right. So in radians and degrees, so in degrees, our arc length is equal to, Ethan?
Our arc length is 15.
No, in just in general, the formula for
Oh,
arc
the
length.
formula for the arc length is theta to the 60 times 2 pi.
But can be simplified to,
Theta times
remember the 2
Oh, yeah.
cancelled, to give me theta over
180
180
and then
pi r. And in radians, Greg?
Theta times r.
Theta times r. Okay. Super easy, right? Super easy. So, what I'm going to get you to do then